So this is more of an observational case study. And so I guess thanks have to go to not only the team there, but the wider team who made the samples available for us to analyse. Now, in terms of, why phosphorus? Got a few meetings there, Matthew. Oh, David. Oh, there we go. Okay, so, well, many of you, or maybe some of you, might be aware that phosphorus is actually a limiting nutrient in terms of freshwater ecosystems. So in terms of streams, rivers, lakes, reservoirs, the majority are actually limited by the concentration of phosphorus. But, of course, we always take a dual nutrient approach to this and never disband an opportunity to manage both phosphorus and nitrogen. Now, another, important reason why we're interested in studying phosphorus in this particular environment is that a number of years ago we looked at historical data over a 25-year time frame that analysed not only soil phosphorus but also the different systems in which that soil was operating within, so dairy versus sheep and beef and other intensities, but then also what the concentrations were in receiving aquifers and also in adjacent waterways. Okay. Now it turns out that in some situations where you have a low concentration of iron and aluminium oxides, but a reasonable enrichment in terms of soil P concentrations, there's a propensity for that P to leach. Now, of course, if it's overlaying an aquifer that has both high transmissivity, i.e. transport potential, but also low anion storage capacity, another measure of iron and aluminium oxides, it can go through there as well. And if it comes up into benthic sediments, it can enrich base flow, and that's where it can have a significant effect on periphyton or algal growth. And you see that in Canterbury quite frequently. Now, so that means that where you have a situation like dairying, which tends to have a propensity of high inputs, on stony soils with relatively low anion storage capacity, and it's either near to a lake or a river, there could be potential for it to flow through the system via an aquifer that can transport it. Now, I was going through the slides this morning and I've got a slightly different conclusion to Cole, and this is my one and only contribution to the presentation, which I'm going to come back to at the end. Right. Okay, so, obviously kicking about in central Otago when I was growing up, I knew the benefits of lucerne and its performance under both dryland and irrigated systems. But to all those, and I can thank all of you nitrogen researchers, I do it a little bit myself, who use the word nutrients because there's more than one nutrient, isn't there? And phosphorus is one of them, and we don't know a great deal about that, especially under lucerne systems. So this being an observational study, I keep mentioning that because we didn't have control of the treatment structures, and they'll be quite important when I come back to the conclusion. But we don't really know what the quantum, both concentration and mass, of P that's leaching through into subsurface and potentially into those aquifers. So we utilised the lysimeters that you guys graciously put in. I'm not volunteering, but I'd really like to see them put in the next time because I can't imagine how it's done that safely given all the stones in there and the size of them. But I can see they're a very valuable resource. And of course, backed up by all the measurements associated with both the inputs and also with the outputs. Now, the treatments were defined, I guess, by the farm management, and that's fine, but it does give it a slight issue when it comes to comparing these two systems, given there are different inputs between the two, and obviously different inputs in terms of, obviously, irrigation. And how that responds to the soil itself is quite important. Now, I mentioned right at the start there are different, characteristics that could lend themselves to phosphorus leaching. Soil pH in most pastoral systems is not one of those because they tend to be at a maximum in terms of both solubility but also uptake. One of them, though, is anion storage capacity. Now, 30 is not too bad, but when you start getting down to the teens, that's when you start seeing exacerbated risk of loss. The benefit, and also, actually they say, the benefit in this particular soil is the Olsen P is quite modest, I could say. Most systems would have an Olsen P of an intensive dairy farm, or even one that's in the top quarter in terms of production, probably around 25 to 30, perhaps up to 35. Maybe that's to do with the stone content and the stone concentration, or it's on a rising plane in terms of fertility. But of course, with such high stone concentrations or contents, that too is a real risk factor in terms of phosphorus losses. Now, the measurements that you guys took obviously were biomass, 9 or 11 harvests, I think, between the two different systems there. And the measurements that we took were largely on the phosphorus fractions. So, filterable reactive P, that's the same as dissolved reactive P. Essentially, that plus a element of filterable unreactive, dissolved unreactive, are available to periphyton. And the concentration at which they evoke periphyton blooms varies on the system, but a previous edition of the National Policy Statement for Freshwater Management had around, I guess, a threshold proposed of around 18 parts per billion, and I'll come back to that. So, in terms of irrigation and drainage in these 2 years that were studied, I'm not a Cantabrian, I've only been here 3 years, I don't qualify yet, but I'm taking that as these 2 years were relatively wet, not only in terms of rainfall, but the low quantum of irrigation that was applied. The drain as a result reflects, I guess, that wetness to a degree, although I would say in terms of commercial operations that's reasonably modest in terms of what was being leached, especially when you compare that to the non-irrigated or dry land site. Most of it obviously coming through of periods when there's moisture excess, either late spring, early winter, and occasionally during irrigation when they perhaps haven't taken into account the forecast. Now, I guess when it comes to the crunch here, in terms of concentrations, if there was a hypothesis that they were different, that wasn't proven. There was no difference between the two in any of the fractions that were there. However, I mentioned a previous threshold of 18 parts per billion. If you were to add together both the filterable reactive and unreactive P, you would have got a concentration of around 20 parts per billion. Hence, that's around an area that could be of concern, and moreover, it is about twice the national average in terms of groundwater concentrations. Most of what was coming out was actually particulate, although I would probably argue because it's a leachate, it's probably more a colloidal phosphorus as opposed to a true particulate that you could probably see. Now, there were no, seasonal variations except to say except for particulate phosphorus, where there was an enrichment probably in the summer. And we can attribute that probably due to the drier conditions and then sudden re-wetting and potentially slaking of soil within the macropores and it coming out in the leachate. Now, because I keep mentioning as a colloid, it's probably going to be more mobile than your traditional particulate P from surface runoff, which is really just suspended sediment. Not only do we look at concentrations, but then also the loading tells us a lot of information as well. The yields, i.e. loads, the Pacific area over a year, were greater in the first year when there was more both irrigation and drainage than in the second year, but more importantly, more in the irrigated than in the non-irrigated site. So despite the fact the concentrations were the same, the yields were different, meaning that it wasn't source limited. So if there was more drainage going through, there was more phosphorus coming out. The particulate P, as you could see there, mirrored the concentrations. Now, in terms of some context. You have to take into consideration different systems associated with each of these studies, but these are all from, leachate studies on grass legume pastures in Aotearoa, probably in Canterbury, but also some in Otago as well. The takeaway message really is that they're not that different under lucerne than they are under shallow-rooted grass and legume systems, both here and probably in Canterbury as well. The one, thing I'll draw your attention to is this study at the bottom here, which is actually the Lincoln University dairy farm. And you'll see there's some stark contrast there. If we look at the loads, with around 40 kilos of P per hectare of P per year applied as fertiliser, about a quarter of a kg coming out, 8 times more that when there was 3/4 of it supplied as farm dairy effluent. Now the treatment structures in this lucerne, trial were from memory very modest, about late 20s in terms of inputs in the dryland or non-irrigated, and might even be less, but it was around 70 in the irrigated system. A lot of that was actually contributed via the farm dairy effluent. Now, the general conclusions are pretty bland here in terms of the overall trial, in that there was no difference in terms of the concentrations. There was in the yields, but that was due to the drainage. Some of it was, reflected erosion from the macropores themselves. And you could draw from that the main conclusion was to limit drainage, and hence you would limit the phosphorus loss. Now I'm going to go all the way back to the start, because this is a young system, only a few years into intensive dairying, a very low Olsen P concentration. I can guarantee if it's being run as a commercial operation, that's going to increase, because most of them will aim to put 25 to have an Olsen P of 25 to 30. In fact, the Lincoln University dairy farm has an Olsen P of around 38 to 42. It bounces around because it's stabilised. However, in that situation, what they had, so nearly over 20 years ago, they started off just like Ashley Dean, ryegrass, white clover though, and this is the data for that plot, or that lysimeter, showing the fertiliser plus the farm dairy effluent, just like it's being applied at Ashley Dean. Started off reasonably modest, but year on year has increased by about 5%, to the point where now it is leaching 1.5 kgs. That's a lot. And if you're thinking that this is going to affect groundwater, I would suggest that this is probably the canary in the coal mine, because even if you started to turn that off, there's still a hell of a lot of a load to come. For nitrate, it might be around 5 years between leaching in the paddock and seeing it in the stream, but for phosphorus, especially via tortuous groundwater flow paths, it's going to be a lot longer. So if you're seeing situations where, especially in farm dairy effluent, because the sorption sites are probably being occupied by the organic constituents, one thing that I would advise you, if this trial was continuing on, would be to start monitoring both the DRP and the dissolved organic P and continuing on from now, because we need more data to say whether this canary is true or whether it's just a parrot. Thanks. Yeah, so the question was, is particulate organic P, i.e. the P that is in organic form and sorbed to particles, important in this particular system? It depends if it's colloidal, Nick. So if it's transportable, then yes. And in the location where it is, obviously feeding into receptive environments, especially where there's a long residence times, such as Te Waihora, that organic P could not only be released, but it could also be mineralised.